Okay, so I'm back. And so now we move on, building on what we have learned on classical mechanics, and we move on to the next subject, traditionally in classical physics, where classical means non-quantum, okay? You know that classical physics, roughly classical mechanics, electrodynamics, that is what we are going to, there you are, is what we are going to do now. And then usually it's thermodynamics or statistical mechanics that probably you don't, do you have a class on that or not? Not, you're going next semester to have one, okay. So these are the three branches of classical mechanics. Essentially physics up to the last century, 1 century ago. So what now? Electrodynamics is a very broad subject, and no way that in 20 lectures I'm going to cover. I mean, we are just going to cover a very limited amount of what we could do. But the idea is to introduce to you the main equations, so that you're going to be able to read a book or papers on the subject, and of course to build on that for your further studies in physics. Maybe it's a good point here to, how much do you know about, do you know the Maxwell's equations? How many of you can you, also, so who knows the Maxwell equation? Raise a hand. So don't be shy, I mean. In principle, all of you should know this stuff, right? Because you have a degree in physics, so I mean. But okay, so we are going to, and of course, one has the problem where to start, because this is a big subject. So where should we start? Usually, well, there are two ways. One, to start from building up the equations, roughly following the historical development. So starting from Coulomb and electrostatics, and then these people with the umbra. I mean, you know, this stuff with the magnetic forces. But I think we don't have time for that. I mean, we are too old for that. So I rather start from Maxwell equations. So I'm going to write the Maxwell equations. I'm not going to justify these equations. You just take them for good. The same way that we took Newton's law, right? We didn't justify why F equal ma. Just take that for good, right? That is true, and then let's see what we can do with that. And so my idea here is just let's do the same with Maxwell's equations, and then derive from those all the possible consequences, among which we will rediscover Coulomb's law, right? This idea that two charges attract or repel each other with a force that inversely proportional to the distance, just exactly like Newton's law of universal gravity. So maybe I write, like I did for classical mechanics, a short outline of what we are going, hopefully, out to do. So I think before Maxwell equations, I write today, in fact, I would like to say a few words about Lorentz force. Because remember that electrodynamics is the Maxwell equations plus the Lorentz force, because the Maxwell equations tell you how to compute the electromagnetic fields, but they do not tell you how a charge moves under the effect of these fields, right? So you need an additional law, a force, that is Lorentz force. Okay, so we start from there. By the way, that was in your final exam, so that's a nice place where you start. Maybe you didn't notice, but the problem there, it was exactly the problem of a charge in an electric and magnetic field. We will redo that in a second. So then Maxwell equations, of course. Then from Maxwell equations, we specify a subset of problems that go under the name of electrostatic electrostatics, so when nothing is changing with time, and of course also magnetostatics. So usually in many textbooks, the authors start from here and build up to the Maxwell equations. So we go the other way. I think it's faster, and after all, we know the answer. So, and Faraday's law, that is a sort of a bridge between electrostatic and magnetostatics. So here you start varying slowly some electric field and discover that you have a magnetic field, because this is the very nice things that we discover either by starting from the Maxwell equation, all building this way, is that the electric field and the magnetic field that apparently are very different, right? I mean, for many years, people never dreamed of thinking that the electric field and the magnetic field were this one and the same things, right? Why within the context of Maxwell equations, this is very much so, because you see that by varying a magnetic field or by varying an electric field, you generate the other kind of fields. And then it becomes absolutely fundamental when we rewrite all these things within the relativistic approach, right? From the point of view of Einstein's theory of relativity, it is and it must be that electric and magnetic fields are one and the same things, because depending on how you move with respect to an electric field, you start seeing a magnetic field and vice versa. So they must be linked. Maybe something about conservation laws. They apply to fields, as we have seen. They apply for the motion of point particles of rigid bodies. So we will study a little bit about these conservation laws for fields. And then we start solving the Maxwell equations, as we did for the Newton's law. And there are classes of solutions. So here I just write some retarded solutions. That means it doesn't, okay, retarded solution, we will see what. And then radiating system, radiating. Because here we make the surprising result that if you move, if you accelerate a charge, or if you move accelerating a charge system, you start emitting radiations, okay? And this radiation is light, according to different frequencies. So then we study these solutions that are plane waves. So you see, Maxwell brought together let's say electrostatic and magnetostatics, and then made the fundamental discovery that when you bring these two together, also light, that apparently has nothing to do with charges or whatever, is just a particular solution of the Maxwell equation. So light itself is unified in this picture. This is really the most important unification of forces that we had in physics. It still stands that electricity and magnetism are the same force, and light is just a manifestation of these two forces together. This still stands. I mean, it's still true. In fact, it's still the only truly unified force that we know of. Because if you go to quantum level, probably you have heard that also the weak forces is unified with the electromagnetic forces, but this is not the same level of unification that you have here. They are similar, but they are not really unified in the same sense that really are the same force as it is here. So after we study a little bit about the plane wave solutions of the Maxwell equations, they asked me to give an introduction about relativity. So we will study the dynamics of relativistic particles and fields. So I assume that you already know this stuff, right? These things about Einstein, right? E equal mc square. But we will do it in a more systematic way, as you may have guessed. And by how do you do that in a more systematic way? By introducing space-time and by describing all physical quantities in terms of 4 vectors, right? As we use vectors in classical mechanics, say, to describe particles. And if you want to do it relativistically, you just move up 1 dimension. You treat time the same way you treat, well, almost the same way you treat the other 3 dimensions. And by doing that, you use 4 vectors or 4 tensors in general. So instead of counting 1, 2, 3, you count 0, 1, 2, 3. And by doing that, you write all your equations in a covariant manner, he said. So this is the correct way of doing relativity for a student of physics. And we do the same for the fields. And if I have time, I would like also to introduce the Lagrangian approach for fields. That is probably what you want to have. Since you know how to write the Lagrangian for a particle, and here we have fields, it seems reasonable to have the same formalism, that is Lagrange equation and Hamiltonians, also for the field. So we'll do that in the four-dimensional notation, okay? And by doing that, we will rewrite Maxwell equations in a explicitly covariant manner, it said, so that we are sure that they are relativistically covariant, okay? After all, Einstein himself started from here because he noticed that remember that our Newton equations was invariant, right? You remember for Galilean transformations. That is, the physics look the same for systems moving with constant speed, one with respect to the others, right? You remember this was a very fundamental law on which we built before Christmas. If you try this, this is not true for Maxwell's equations. So this was the basic observation. You had 2 sets of equations, Newton's, Maxwell's, and Einstein, check, and well, not just Einstein, everybody knew that Maxwell equations were not satisfying the same principle of Galilean invariance that Newton's law did, okay? So this was a puzzle, right? You had 2 nice sets of equations describing all the physics you knew, but they were not the same because some were described from one invariance principle and the other. So which one one of the 2 had to, it's like now people talk all the time about quantum mechanics and gravity, right? Probably you heard about that. You have quantum mechanics that works very well and gravity, that is Einstein's theory of gravity that works very well, but you don't know how to put them together, okay? So this was exactly the same problem conceptually. You had the Maxwell equation describing perfectly well all we knew about electrodynamics, and then Newton's law, or Lagrangian equations, whatever you prefer, describing very well classical system of particles, springs, and rigid bodies, or this kind. But they looked different. You could not put them together. Okay, so something had to yield. I mean, which one is right? Okay. And here's the same question with quantum mechanics and gravity. Is quantum mechanics correct all the way and then gravity has to be modified, or vice versa, quantum mechanics at a certain tiny level of very small distances, it has to be modified to give rise to gravity, okay? Well, nobody knows. Maybe one of you will provide the answer. And here, probably most people put their money on Newton's because, I mean, that we knew that, well, I mean, F equal ME, I mean, how can it be wrong? But actually, as you know, the other way around is the correct one. That is the Maxwell equations that are invariant on the Lorentz transformation, not Galilean transformations, right, are the correct description of nature, and Newton's law is not correct. You have to change Newton's law. Okay, so that we will discuss a little bit about this theory of relativity, about which, again, I assume you already know, but you know, it's nice to study something that you already know because you feel comforted in your knowledge. So we will do a little bit, not much. I mean, that again is a subject. We will discuss a little bit about Lorentz transformations and how you modify some of the classical equations to allow for relativity. Okay. So maybe we'll say something about the paradoxes, because of course it's not so obvious that this is the correct transformation laws, because you know that there are things that do not seem obvious when, for instance, the fact that the velocity of light is always the same, no matter the frame of reference that you are using, right? That is completely against Galilean transformation, because obviously if you are on a car moving 100 kilometers per hour and you turn on your lights, according to the Galilean transformation, light from your headlights should move to the speed of light plus the 100 kilometers per hour. This is obvious, and of course it's not true. So one has to. So you have all those paradoxes coming from that about dilatation of time and length, so on and so forth. It is just that we are not used to, since our life is in a regime in which the speed of light is very much higher than all the speeds so we are not used, our mind is not used to this kind of Lorentz transformation. It's much more used to the Galilean transformation, even though that too are not so obvious, because remember what we discussed many, many times, that if you push something and you stop pushing, most people will say that if you stop pushing, the object will stop, right? Why we know, I hope by now, to have hammer in your head these things, that if you stop pushing, the thing keep on moving. This is the Galilean invariance, okay? So even that, or maybe I think I really believe that it's more revolutionary, the Galilean concept that, you know, if you stop pushing, the things keep on moving, that is F equal ma, you know, it's more revolutionary than the Einstein's idea that you have to use Lorentz covariance. Because if you accept that, then it's a little step to go to Lorentz covariance. Okay. And so after having done this, I think we, well, I don't know if probably we won't have the time, but I would like to go back to the problem of the radiation by a moving charge, so that we do it in a four-dimensional way. That is the correct way of doing it. Okay. Of course, many things are left out. There are many things. Well, but you can find most of these in the textbook that I suggest. That is Jackson's, I think, classical electrodynamics. So as I already told some of you, this is like the Goldstein classical mechanics that I suggested in the classical mechanics class. This is sort of the textbook that everywhere in the world is used. I mean, any student of physics know a list of these two books, the Jacksons and the Goldsteins. Okay? It might be Landau's, I don't know. But they also, this is nice because it's the common knowledge. Yeah. You can read what I... What? Radiation by charge. Yeah, it's hard to charge. Yeah, I guess. So it's a part of being a physicist to belong to this community. At least there are these two textbooks that every student have studied. And so this is a bit complicated. Some of the chapters are a little advanced. I think we are not going to discuss those chapters. But all the rest, you find it there. And more or less, I will follow that textbook. Unfortunately, the problems, the exercises of this book are very difficult. So if you thought the Goldsteins were difficult, these are really difficult. So I didn't know what to do. I mean, they are interesting, but I think a little too difficult for us. So I think this time I'm not going to assign problems from the books. Each time I will write. So I think I take the problem from these other books that you don't need to know about. And I will write here the problems, and then you solve it, and then we solve them together as we did the other time, okay? Okay. We try. This is the first time that this class is given, by me at least. So we try and see how it works. Okay, questions? Please. How much? I think 20 classes, so that means formally 40 hours, but since here the hour is like 45 minutes. It's a relativistic effect, right, already. So we'll see. Let's see. I think roughly that, 20 classes. You don't need more. I mean, you don't need to know everything about this. I think you need to you know, it's like classical mechanics. We didn't cover all the subjects. Some we really sort of surfed through, but I hope at least you have some ideas, some fundamental ideas. I hope I taught you about those, and here we do the same. This way you have the tools to move on to more advanced subjects, but you will always come back. I mean, in your professional life, you will see you will have to go back to this book because you will meet things that we haven't studied. It's not working, or you have to or. Se no lo metto. Perché batte sulla camicia. Ok. Other questions, please? Louder, because I'm a little. Will
we have classes for exercises?
Yeah, I think I don't know, did you like the way we did it for classical mechanics? If you like that, we do the same. That during the week, I give you some problems, then you solve them, and on Monday, we solve them together. If you did not like that, I mean, it's nice, I think, but it's time-consuming. So if I do the problems, it's faster because I read the solutions in the book. But I think it's good for you to try yourself. So let's try it this way. We will see. So my idea is that, again, I give you the problems. Then next Monday, for instance, we start, and you solve 2 or 3 problems. And then, so 2 classes for the theory. But as I said last time, the problems are also the theory. I mean, it's not that in physics. It's not that you have the formal stuff and then the problems. Much of the formal stuff is really hidden in the problems, right? Because I can write the Maxwell equations, but until you solve those equations in some specific problem and you get the feeling, you don't know the Maxwell equations, okay? So you must, you see, here is a very good testing ground for this idea that you know a physical equations when you sort of know the solutions without having to solve it, okay? You always have, it's like the harmonical oscillator that I've bored you for months before Christmas, but I hope now when you see the harmonical oscillator equations, you already see the solution, right? I hope. Because for you, these 2 things must go together. When you see dot, dot, and then something, you already must see this cosine and sine going up and down, okay? And this is the idea. When you see the Maxwell equations, you already see the solutions, okay? The waves, for instance. Okay, other questions?
I want just to know the difference between electromagnetism and electrodynamics.
The difference? No, there is no difference. It's just name. I think electrodynamics is more, I don't know, is sexier than electromagnetism because this idea of dynamics, right? You have these particles moving around, but I don't know. It's just me, probably. Okay. It's the same thing, electromagnetism and electrodynamics. And I should stay below this line, right? Okay. So as I said, let's start with something that we are sort of familiar with. That is, so Newton's law, right, is this. No questions about that, I guess. And so then the step that now we move to the next step is that we decide what the force is. Up to now, we have taken some strange system where F was either due to springs or to gravity or some stuff like that. And essentially was some macroscopical forces. Now we specify our force to be what is called the Lorentz force, that, as you know, is the charge of your particles. So now the particles, this ideal point particles, is characterized not only by having a mass, okay, but also a charge, okay, a new property of these point particles. So I skip all this discussion, you know, what is the charge, how you measure the unit, you know, the Coulomb. This is very boring, and you are going to forget every time you have to check on your textbook about what the units are. Let's just take that the fundamental object that we are going to study is again the point particle, if you wish. Then we will generalize to distribution, continuous distribution of charges, like we did for the rigid body. That was a sort of a continuous distribution of mass. But so for now, let's study the Lorentz force for a point particles that is characterized by the mass, simply because it has a mass. So here you have m times the acceleration, but also a charge, that is the charge. After all, we didn't discuss much what the mass is, right? This philosophical question, what is the mass? And here the same, you just have the charge. Charge and mass. These are the two fundamental quantities that characterize your, think of an electron, for instance, if you like. And the electron is just a point particle is characterized by two charges, the mass and the electric charge. And then, if you remember, there is the electric field, and then the magnetic field that is a little weird, is the weird guy in this equation because he comes with this vector product with the velocity. So this is what is called the electric and this is the magnetic field. And this is the velocity. And of course, there is this very annoying thing about the units in electrodynamics because you have many systems of units. And this is always the bane of many students because you have always to remember in which units you are working on. I'll come back to this. But this equation is like this in what is called the international system of units, right? Did you study in these systems or the Gauss system? Or the CGS system that is like Gauss in this case? In that case, if you are using Gauss or CGS, you have an extra 1 over c, where c is the velocity of light. From now on in your life, for you, c is always, I don't know really why they call it c, but maybe because it's constant, I don't know. But anyway, c is going to be, don't be that student that at the end of a class on relativity ask, what is c? That really kills you. So c, it appears here. So the Gauss, well, I'll come back to these things about the units because it's complicated. And it's really not essential. But so let's stick to this international system of units. And so there is no C there. So what can we say about these equations? Okay, first of all, notice that you see the force is given not in terms of the physical quantities directly, but rather through one step mediated by this new concept of fields, right? Instead of telling you that this force is proportional, like in a Coulomb force, right, the product of charges, I rather tell you that I tell you what these two fields, the values of these two fields anywhere in space, okay? And then if I've given you these two fields, vector fields, notice, then you know how to compute the force, okay? This is the idea. And this is a very, okay, it's a small step. It looks like a small step. It's a little bit how we did it for the gravitational force, right? We didn't study the gravitational force by telling you that if you have a mass, it attracts the other mass, attracts, let's say, with a force. We introduced the potential that gives you the value of the potential everywhere in space, and then the force, the gravitational force, was the gradient of the potential, right? So we used the potential not to describe the force. So you see, it was like intermediate steps, but it's very useful. And here is really the development of this idea to the n powers, because everywhere you specify two fields, the electric and the magnetic fields, okay? And once you know that, you know the force, because you use Lorentz force. So this is Lorentz. And as I said, this is a very, you see, this looks like a small step, but really is the beginning of modern physics, because modern physics is made of fields. The idea is that everything in nature that is fundamental, all forces are really fields, okay? And I don't know if you appreciate the difference, because before you had forces that, like, for instance, Coulomb force. The Coulomb force tells you that if you have a charge here and a charge here, they attract or repel each other with a certain force that is proportional to the product of the charges and inversely proportional to the square of the distance. But you see, this is a description in which you take two charges, even infinitely distant, and instantaneously they act on each other, producing this force, right? So this is the idea. Also, Newton's law of gravity is the same, right? You have the sun there and Jupiter there, and instantaneously they act on each other. But here is a very different approach. Here, I don't tell you what happened very far away. Everything is local, because this is the force at the point x and the time t, and this is the field at the same point and time, and this is the field at the same point and time. Everything is local. There is no instantaneous action, okay, or interaction. Everything happens locally. You know what the value of the field is here, and you know what the force is there, the same point, okay? So everything is local. This is really the mantra of modern physics. There is no action at the distance. Everything happens because nearby something is changing, okay? And therefore, remember, if this is the case, you can describe it using differential equations, because differential equations tell you how something changes a little bit away from where you know how it's behaving. And in fact, the Maxwell equations are going to be differential equations, okay? Vectorial differential equation, but still differential equation. So this idea of writing the force through some fields and therefore describing everything locally is very important conceptually, okay? Even before we start solving this equation, because it allows us to describe the whole of physics locally. Everything happens because it happens in that point and not because of action at the distance. This is still important today, okay? It's still important today. And there is a nice book that you may like to, that Einstein himself, together with Infeld, who was a colleague, they wrote a sort of a history of physics that is called, I think, The Evolution of the Physical Law. You find it in the text. It's a very nice, very simple book that you can read and enjoy. And essentially, he describes how this idea of field develop and from very specific example to dominating the entire understanding of the physical world. So that's a nice reading. I remember when I read it, I was very impressed. So let's study two simple examples of how this motion. So what is the motion of a charge under a given electric and magnetic field? Of course, the simplest example is if we take this field to be uniform and constant. Okay, so let's just stick to this very simple example. You have a charge, okay, so with Q and M, so a particle coming in a region in which there are uniform and constant electric and magnetic fields. How is it going to move? Okay, so a particles come in a region in which, for instance, is like the CERN LHC is exactly this example. You fire a proton that is a charged particle with the mass of the proton, and then it goes inside the tunnel where there is, in fact, magnetic and electric fields, and they are made in such a way that the particle is curved and it goes around, right? By nature, the proton will go straight, but because you have a magnetic field, it will curve, and because you have an electric field, it will accelerate. So that's the basic idea of these big accelerators that people use to explore the fundamental particles. So what is, so let's write this Lorentz force for this specific case. Let's start with, let's first do it for the simplest case. And I guess the simplest case is, well, I mean, you see what is going on here. The electric field, right, so we have a uniform and constant E and B field. So as I said, the simplest case. And maybe we can start first with a constant and uniform B field. What happened? Let's take E equal to 0 for the moment. And what happened to the equation? Well, you see, it's very simple because you have D. So you have this dot P. So you have dt and V, right? Equal. So you don't have this term. So you just have. So I guess I put. Well, I like it to do it in the well, it's up to whatever. Q so V cross Q, right? And then you have the B that is constant. V cross B, so Q cross B. And then here, the mass, I take it to be constant. This is not strictly true if it's moving really fast, but for the moment, let's be non-relativistic. So here I have the derivative of the velocity, usual. The mass, I take it on the other side. So I have this quantity V cross, say, QB divided by M. And then maybe you have a C if you are using the Gauss units. You don't have the C if you're using the international units, okay? But let's put the, so this is like this. And this is usually this is written in this form, where you introduce it. You see, this is like an angular velocity is called, where the modulus of this is this QBMC. This is called the gyromagnetic rotation. It's a constant for that for this equation, okay? Because B is constant, so I mean this quantity is really called the gyromagnetic ratio because this is characteristic of the particle. You see, once you give the charge and the mass of the particle, that ratio is given, and then you compute by multiplying by B, you get the quantity. So you see, this looks very much like the, yeah.
What is it that you have done here?
Where?
Because according to that equation, we already have a force.
We already have?
Yeah, from the equation. From the Newton's equation.
Yes.
Yes. The electric field is already surfacing up.
No, the electric field, I put it equal to 0. I do it step by step. Then we turn it on. I just want to see how the solution looks when the electric field is 0. Notice, yeah, okay. Notice one thing that remember the magnetic force does not do any work. You see, you understand, right? Because you see that you see B is always orthogonal to the direction, so it's not producing. So all the work is done by the electric field.
I want to know how we can define B when we have E. When the velocity becomes variable, and then we can find.
No, now I just E and B are given. They are external fields. So okay, maybe this is. So here I'm studying. The Lorentz force gives you the motion of a particle for given E and given B. But E and B are external. It's not the electric field and magnetic field generated by the charge. These are two different problems. But of course you are correct. Here I should include also what happened because I'm accelerating a particle, so I'm generating. But this will do it at the end of these 20 classes because it's a complicated problem. But here, this is like a point particle in the gravitational problem. You don't compute the effect of the mass of this particle on the gravitational field. You assume that it's just an external gravitational field and you study the motion. This is why it's called a test particle, right? Because you don't compute the back reaction due to the presence of the particle in the field. This is a useful concept. So this for us is a test particle. That is, I do not compute the back reaction on the fields sorry, due to the motion of this particle. Exactly as we don't compute the back reaction in the gravitational problem due to the mass of the test particle. That's why it's called a test particle. Okay. So again, I'm taking E equal to 0, so I have a sub-problem that is simpler. And you see that this is so if I write the component of this, I take, you see this is a vector product, okay? So I take let's take the B field in the Z direction, okay? And therefore, you see that you have the V dot X equal this omega B, the Vy, okay? And the V dot Y minus omega B Vx because of this vector product, right? And then in the Z direction, where you have, you see, you have no component. So the V dot is equal to 0, right? If the B field is in the Z direction, here it gives 0 for the Z, so you have this. In the other two directions, the two perpendicular directions, you have these two components, and they come with the opposite sign because of the rule of the vector product. So that's the equation, but this is rather simple if you want. So this is trivial, right? But also this, it's rather simple because you see that if you introduce the complex quantity Vx plus Ivy, right, you can bring these two equations in a single equation because it's just the time derivative of this complex number must be equal, if you look, minus I, right, because this, and then this Vx plus y omega b, right? So it's similar to what we did for the harmonical oscillator. In fact, this is essentially a harmonical oscillator. And you already know, exactly because it's like an harmonical oscillator, the solution of this is going to be that this quantity here is some constant, let's call it A e to the I omega B t. Right? This is the harmonical oscillator. And I solve it. You remember how we did it for the complex? A nice way to solve the harmonical oscillators is to introduce a complex amplitude, and this is the solution. So it's an oscillating solution, and if I write it back into the real component, so you see that the Vx is the real part of this number. So you see that the solution is that Vx is some constant V0. So it's the real part, so it's the cosine of omega bt plus some initial phase, right? While Vy is the imaginary part, so it's this V naught, maybe it could be the minus because of the I. It goes like the sine of omega b t plus alpha. This V naught, you can check, has to be the Vx square plus, well, is the square root of Vx square plus Vy square. You remember this way of solving the harmonic oscillator? Vaguely. Well, and because you have the velocity, then is very, I can just integrate, right? I just integrate once with respect to the time, and I get the trajectory. So some initial position plus some r that so r is this v naught divided by omega b, right? Because I'm integrating, so I have to compensate for the omega b factor. And then the cosine becomes a sine because of the integration. And similarly, I have for my y component now with the cosine. And as I said, the z component, that is the z of t, is just, well, zero acceleration, so it's just some z plus some v naught t. Okay. So how does this trajectory look like? So you see, it's very similar to the problem you had in the final examinations, right? Because you had a Lagrangian that gave you equation of motion, a part of which was in this form here. But you had also the electric field, so we are going to do the full. How does it, so you see, this part here is telling you that it's an harmonic oscillator, so it's just moving in a circle, right, of radius r with the angular velocity or frequency omega b, right? So if this is the B field, this particle is moving like this, but is also translating along the direction of the B field by a constant velocity. Okay, so it's something like this. It's a helix. So it moves like this, and at the same time moves if there is with this initial velocity. Is this clear? So that's the typical motion of a charged particle in a constant external magnetic field. It just moves with in a closed orbit in the plane perpendicular to the B field. These orbits are called Landau orbits in quantum mechanics. Probably you have you studied this problem in quantum mechanics? Oh, I'm sure, yes. Possible that this is a very important problem in quantum mechanics, that you have these orbits, and the point is that in quantum mechanics, these orbits are quantized. These are the Landau orbits of the motion of a particle in an external magnetic field. But here they are not quantized because it's classical electrodynamics. So essentially they move, you see, like this, and if there is a component in the direction of the B field, then it translates with constant velocity in that direction. Okay, yes. Yes. No, I think this is the initial velocity. This is the initial velocity in the z direction. So it's another something like this. If it's not moving, it just moves like this. So you see, it's a sort of trapping of your charged particle, because if you put the magnetic field, then the particle is going to remain in this channel. So you see the magnetic field is bending the trajectory. It's not doing any work. It's just bending the trajectory of your particle, and that's a way to contain the particle, right? Because by putting magnetic field, you keep on bending this particle, and it stays within that volume, okay? So what happens if I turn on the electric field also? So we have two. Let's solve. So can I erase that? So we go until 5:30, right? Or I forgot. It's 5:30, right? Ah, well. So let's take the. So maybe let's solve it again in the case. So you have the B field. Or something like this. So now I turn on also the electric field. I want to see what is the complete solution. So I keep, so this is the Z direction. I keep the B field in this Z direction, okay? There. Then you have a X and a Y direction, something like this, okay? And I take my E field, I take it in the ZY plane, something like this, okay? So that there is a component, like this, there is a component E in the Z direction, and then there is a component in the Y direction, that is this one, okay? So the B field is here. The other field has a component that is perpendicular to the B field, and then a component EZ that is in the same direction as the B field, okay? So I take my two constant fields in this configuration. And but therefore, if I look here, so let's write now explicitly mx dot dot, m y double dot, and mz double dot, okay? So this part. I have, so I guess I said we use Gauss, so I have this C. So I have to do in this direction, you see, the E field is in the ZY plane, so there is no component in the X direction. So for the X is exactly as before. I have Q over C, B, that is the BZ component, but B is only in the Z component, and the velocity Y component of the velocity. So it's exactly as before, because there is no electric field there, okay? Now in the Y direction, you see now I have something slightly different, because I do have EY component in that direction. So I have, as before, minus QC B X dot, but I also have a component coming from here that is just Q E Y. Okay, so this part here is exactly what I wrote before. I just wrote the velocity before because I wanted to get the answer quickly, but these are really the Newton's equation in this case with the acceleration. How about Z double dot? Now before that was 0 because there was no field in that direction, because B was in that direction. But now you see I have a small component, well small, whatever component I have of the E field in the Z direction. So here I should put E Z component in that direction. So because of what we did before, it's rather simple to solve this system. You see the change in the z direction is that before I had this uniform motion with constant speed, but now I have an acceleration because you see the acceleration is not equal to 0. So the charge, even in that direction, is accelerating because of the E field in that direction. That characteristic of the electric field, the electric field is doing work, is really accelerating the charge. So if you want to accelerate the charge, you need an electric field. If you want just to deflect the charge, you need a B field. This is you know, the secret of the Lorentz force. Okay? And the other two components are almost the same. The only difference is that you have this extra term that clearly is going to produce a sort of a drift in that direction, because you see that I can rewrite this equation as before. So x dot dot is equal to the omega b, this qb over mc y dot. So I have these two components that looks like the harmonical oscillator, these two. But here I have a slight difference because I have this extra term that is this one here. I have q over m times the component of the, and z is again a q over m times z. So the acceleration of a charged particle is controlled by the value of the charge over the mass, while the rotation radii of the in the magnetic field is controlled by this angular frequencies omega b. Okay, and these again are rather simple to integrate. These are really, if you look at this is really what you had in your exam. I hope you recognize. I just call this A and this B, I guess, not to confuse you with the charges. And so this is exactly the problem that you had there. And so I assume that you already solved it for your problem, so I just write the solution here. So this is trivial, right? You have to integrate a uniformly accelerated charge. So this goes like QEZ divided by 2m t squared plus whatever the initial velocity is, plus the initial position. But let's assume the initial position is somewhere here at the origin. You know, that's like 1/2 gt squared that you have in gravity. The only difference that here, instead of having g, you have this quantity. So this is a charge is uniformly accelerating in that direction. The other two are similar to before. So xt, you have the harmonical oscillator solution, right, like the one I just erased, with a sine omega t plus some initial phase, and the yt, that is just the same stuff with the cosine of omega t minus some constant. I put it here just to normalize. But you have an extra piece here because of this, that is just this c e y v naught omega t. So this part here is this rotation going around as before, but at the same time you have a little shift in one of these due to this extra part, due to the electric field in that direction. So the orbit is a little bit more complicated. You have, because of this, this term is called a drift, right? Because you have a drift. So it's not very easy to describe this motion. So before it was just like this, and then maybe moving as a helix. Okay. Now, even in the x, so before in the xy plane, it was just like this, right? Then, if you had the component in the z direction, this circle was moving, producing a helix. Now, even in the xy plane, you see it's not just the harmonical oscillator, you have this shift. So it's something like this, right? So you see you have a drift. So it will go like this, but because of that term, it drifts So it doesn't come back here neatly. It goes like this. And then if you have the Z, this thing is sort of move up. So you have to think of this and then moving up in the Z direction. Okay, can you see that? Or I have here a computer simulation of this orbit, but, well, I don't know. You can try. It's done with Mathematica, so some of you like the program. So, but okay, so if you put the Z component, then you tilt this thing out in the Z direction, and so it moves like this, it comes out, and it's accelerating in that direction. Okay. Questions? This is the solution. This is the solution for this is the orbit. No, the solution, this is the full solution. Not together, yeah. No, this is the solution of this system. And the way to get this is as you did in your problem, or as you did not do. That you see, the way to solve this, well, they are this is trivial. This, you have to notice that, this is like, you have the x dot, you integrate this once, and then you put it back here, and then you integrate that, and you get this. Okay. So that's what I wanted to say about the Lorentz force. We will come back to the Lorentz force further on. But in this remaining half an hour, I want to introduce the Maxwell equation so that I'll do it and then we stop. So you see, I mean, the motion is not very complicated. Yeah, it's. In 4 dimensions. Now this is 3 dimensions.
What is the form of the Lorentz equation? Lorentz force
In 2 dimensions, just the Lorentz force. So you want to solve the equations just in 2 dimensions. You can do that. Everything must be there, right? But I mean, this is no.
No, because the nature of V equals B.
That's a nice question, actually. Yeah, now I understand. Yeah, this thing exists strictly only in 3 dimensions, right? But there is another thing that you can have in 2 dimensions, but I'm not sure that we want to discuss that. I mean, this vector product is actually, as you said, defined only in 3 dimensions, because you need, in 2 dimensions, you have to introduce another things. So, okay, now I see your question. But don't worry about that. I mean, this is artificial. Well, it's not so artificial because many materials are almost 2-dimensional, right? So it's interesting to study this in 2-dimensional systems. But, okay, yeah. So if you wish, 3 dimensions is the smallest number of dimensions in which you can do this in a straightforward way. So that might be why we live in a 3-dimensional world, right? So that we can have Lorentz force in this form. This is a long-standing question, why there are 4 dimensions instead of 10 or... Have you ever considered this problem? Clearly, 2 dimensions are is not enough to have organize life in a way, right? You really need three dimensions to have a brain, because 2 dimensions you understand, I mean, right? So, but from the physical point of view, of course, the brain is not necessary, so one may wonder about lower dimensional worlds, but okay. Okay, so if you don't have any other, so we'll come back to the Lorentz force, but only after we have said something. So the next question, if you wish, is here I have, so let's erase everything. Maybe a question you could have asked is why I don't use the Lagrangian, right? Since I insisted so much about Lagrangians. So, but in fact, true, good questions that I ask myself. In fact, we are going to use the Lagrangian. Of course, you can write this force, these newtons, in terms of Lagrangian equations. The trick is that easier, in fact, actually, you cannot use E and B. You have to use some potentials. So to do that, I first have to develop some idea about E and B, introduce the potentials, and once I have the potential, I'm going to write the Lagrangian for the charged particle. So if you ever have wondered. So it was not a waste of time to study the Lagrangian, but of course everything has to be recasted in that language. Yes?
What will happen if the velocity of the particle is constant, but there exists a magnetic field?
No, the velocity is constant, it's okay.
What will be happening?
No, but
I have a particle which moves with constant velocity.
yes.
But the magnetic field is not zero.
Then you just, as long, if V is different from 0, this is the force.
If V is a constant.
No. V initially can be a constant, but then you have to put that as initial condition, then you solve the equations and you see whether it remains constant or not. Right? You cannot impose, you say, what you impose are the initial conditions. So you say, okay, I take a particle with constant velocity, fine.
Yes.
Then I plug in here.
Each time.
No, but you cannot tell the particles what to do after the initial conditions, because then that's the solution of the equation of motion. To be consistent, then, if there is an electric field or something, it will accelerate. I mean, you can turn the thing around and say, what are the B and E fields such that a particle remains with, yeah, well, that's it. You solve the equations then. But in a way, you already know this, because B is not going to change V. It's going only to change the direction of V, but not the because it's not doing any work. So unless you have a E, the absolute value of V remains constant. You see, B is not changing V. B is only changing the direction. Okay. So now we concentrate on these two quantities and try to say something. Well, C goes and come, depending on the, so back in the SI units. So as I said, the discovery here is that the simplest way to write the Lorentz force is not through telling the system where all the other charges are and how they are moving, but simply I assume that all these other charges, by moving or by simply being there, generate two quantities that I call the electric and the magnetic fields. And then at that point, by using this Lorentz force, I can compute the force acting on the test charged particles coming into the system. Okay. So these two are, as I said, so these two are two vectors. So they are fields, vector fields, okay, in space-time. we may as well start thinking. That is, I have E for each point. Let's use Cartesian coordinates, x, y, z, and also at the given time, and B, x, y, z, and t. So all the physics is controlled by these two vector fields. If you know these vector fields, you know the force, and so you can solve your problem, as we just did in the case of two uniform and constant electric fields. Okay. So the problem now is how I can compute these two quantities by knowing okay. So if you know these two quantities, you can compute the force. In fact, you don't care at this level of what exactly the distribution of charges and how they are moving, those charges that are produced in these fields. If two distribution of charges, even different from each other, produce both of them produce the same electric and magnetic field, then you are going to have the same force, okay, independently. So you have decoupled these two problems, okay. And the other important property is that you see you have a superposition principle, okay. This will become clearer when we study Maxwell equations. But if you have two distribution of charges and you know the solution of one and the other, the solution when you have both of them is just the addition of these two fields. So the electromagnetic fields follow a superposition principle. That is, this will come from the fact that the Maxwell equations are linear in the fields. Okay, so there is no interaction between the fields directly, field to field. Okay, this is not always true. You can think of many other systems in which you have that, but this is not true for the electromagnetic field. And this was not true also for the Coulomb, or for that matter also Newton's law, because remember that if you had the three-body problem, for instance, charge Q in the field of charge 1 and Q2, the Coulomb force on this charge is just the sum of the force of this plus the force of this, right? It's always a two-body problem, exactly because, like it was in gravity, because of the superposition principle. If you have one solution, if you have two systems, you just sum the two solutions, the two forces, and you have the force of the system. There are no peculiar three-body effects. There is no a piece that depends on Q1 and Q2 together, okay? But please remember that this is not obvious. It's a particular property of these fields. You can think of other fields in which this superposition principle is not true, okay? Then you have nonlinear effects on your equations. For instance, gravity is not exactly of this form because there are nonlinearity in gravity, and you have to take that into account when you consider the general theory of relativity, okay? But for electromagnetism, this is true. It will be reflected in the linearity of Maxwell equations, and therefore, if you have two distributions, you can just sum them up in the fields, and the force will be the sum of those effects. So these are vector fields, okay? By the way, this is the reason why light does not interact with light. Exactly because of this property, if you have two beams of light and they shine across, they just go across. There is no weird interference with light. You cannot deflect light by using light. Is that clear? Like in Star Wars, where they have laser swords, that's clearly nonsense, because if you have two lasers, they just go across one. Is that clear? No. Light does not interact with light because of the superposition principle. So if you have two beams, two laser beams, they just go across. So if you have a laser sword, like in Star Wars, they would just go across because there is no interaction between these two. So that's a neat trick, but it's not true. You need a nonlinear field if you want a laser sword, like what's his name? The black guy, the Vader, Dark Vader. So it cannot be light, okay? So this principle, so I hope this will fix that it's important to remember that here you have superposition principle, so light does not interact with light, exactly because light is made of electromagnetic fields. So these are vector fields. So vector fields are stuff like this, right? At each point, usually you draw a vector field by drawing these force lines, are called. I think Faraday was the first guy who started thinking of vector fields in terms of force line, meaning that for instance, the field here, you see, is the tangent to this line, okay, in each point. So if you follow the tangent, you can draw a line, and this is called the force line, because in this case, it gives you also the direction of the force, not in the case of the magnetic field, though. So that's a nice way of thinking. If you have a vector field, think of these force lines filling the entire room, and that is the configuration of the field. And this is a nice thing about electrodynamics, is that it's very visual. I mean, you really have to produce these pictures, and if you understand these pictures, you understand the Maxwell equations, as I will show you in a second. So if this is the, so another way of think of this is the velocity field, right? A typical, if you have a fluid like water, you describe the fluid, water, by a velocity field. That is the velocity of water at each point in the fluid, right? So you have so this is like the stream, the current in the water described by the velocity at each point that is tangent to this line. So you see the river flowing, and the river flowing represent the vector field of the velocity at each point in the flow, okay? And here is the same. The electric and magnetic fields are flows of these quantities in space, okay? So like underwater. And actually, this is the way Maxwell visualized most of these, but you will see that is a very strange fluid when we start writing the equations, and you will see in a second. It's a strange fluid. And in fact, at the end, this idea, because have you ever heard about the ether, the thing that filled the entire universe? And people thought, because light was thought as waves of these electromagnetic waves, electromagnetic fields, but you know that the wave to be there needs some substratum, some medium, right? If you have you hear me talking, because the air in this room is compressed by my voice, right? So you have air, and the air is carrying the sound waves, and the same in the sea, right? But here, if you had electromagnetic waves, you needed something. This something was called the ether, because you needed something to go up and down somewhere to carry the wave. And we'll come back to this, because clearly there is no such thing, because light is carried across the vacuum, empty space. So what is going up and down is not clear at all, okay? But for the moment, just think about these fields as velocity fields. So you have this room all filled with the fluid, and you have these velocity fields going around, and you have two of those, E and B, okay? Now, how you quantify this? This is a nice exercise in mathematics. So this is the picture. Now you need some mathematical tool to quantify, for instance, when these lines become very thick, right? Or when they go around. And you know from your class on, well, I don't know, you did some vector calculus, right? So you know that these tools are there, and there are essentially so two tools. One that quantify the flux, so how much of this stuff goes through a given surface. So you need to know what is the flux, right? So how much stuff. So the idea here, so I'm not going to do, did you do that with Narayan, or the divergence, the curl? Yeah, you did. You did not. You did or you did not? No? but you know what that is. So I'm not going to do it mathematically. I will do it from the point of view of a physicist, so the poor man mathematics. So, but then I mean, there is a rigorous way to introduce this, and you are welcome to go to the textbooks, but we don't have time, and also probably I don't know, I wouldn't know how to do it really as a mathematician. But okay, so I said the first thing you want to quantify if you have this flux is how much of this stuff goes across a given surface. So you have a given surface, right? And you have this stuff going through, okay? And you see that what you need is the flux of this velocity field. So this is, the flux is the average normal component, right? So if you have a line here, line here, line here, you take the normal component to this surface. So you project out the component. This is going like this. The surface is like this. You project out the normal component. You take some sort of average, normal component, and multiply by how big this surface area. So this is, is the intuitive way, idea of a flux. If you have water coming through, you take a surface, you compute the normal component of the velocity going across that surface, you multiply by the surface area, and this is the amount of water that has gone through. That is the flux, right? You agree? So we need the flux. And then the circulation is called circulation. That is the other quantity that I'm interested, because I want to know if you have here a lot of lines, as I said, or very few. This is the flux, high flux, low flux. I also want to know how much of this stuff goes around, doesn't go straight. And for this, the idea is that I take a curve in space, okay, and then I take the average of the tangential component. So if here I have this, here I have this, I take the tangential component of my velocity field, average tangential component, times the distance around. So how big is this circle? So with these two ideas, flux and circulations, we can write Maxwell equations, because Maxwell equations are telling you how much flux and how much circulation of the electric and magnetic fields are linked together in a given situation. Okay?
Is that right? I mean, when we say flux, it means like the number of the field lines per unit area center.
Yeah, the orthogonal, the normal component.
Yeah, so we should divide by the area.
No, at this point, let me leave it like that. Then we do it properly. No, this becomes, if this is bigger, it becomes bigger. It's not by unit. You understand that here I have an integration over the surface when I go differential. And here I have a line integral along this, right? Okay, so we will get there. But this is the intuitive things. So with just these two ideas, let me write Maxwell equations, and then next time we write the mathematical expression for this. But as I said, the best way to understand Maxwell equations is by this picture. So here, laws of electromagnetism, aka Maxwell equation, also known as So the first one tells you something about the electric field. and if you already know them, you know, it tells you that the flux of E through any closed surface, so you take a surface, closed, flux of E through any closed surface is equal to, who wants to, yeah, the net charge inside the surface. And actually, because of the units, you divide by this quantity that is called the permittivity of vacuum, something like this. But the first idea is that, so you take a closed surface, and the net flux of electric lines is proportional to the sum of all the net charges, so plus, minus. Remember, the charges, contrary to the mass, come in two varieties, positive and negative charges. Net closed. So if you have a surface with no charges inside, you don't have any flux of E through the depth. This is as completely equivalent, as we will see shortly, to Coulomb law. It has to do, in particular, with the 1 over R squared dependence and other stuff. Yes?
So, if it is for closed surfaces, and they say inside, say closed conductor, there is no charge, does it mean that the flux lines don't pass the conductor?
No, it means that, say you have lines like this, but not originating inside. Then you take a closed surface, then they compensate. So the flux that comes in is equal to the flux that goes out, so the sum is 0. That's why it's equivalent. This is, well, is that clear? If you want a net flux through this sphere or whatever, you need to put some charges inside. Then you have lines coming out this way, right? And then you have a net flux through this closed surface. It's a closed surface, not an open surface. If you use the language of fluids, that means that you need a source of fluids in order to have a net flux through a closed surface, right? If you take a sphere, you put it in a river, if there is no source of water inside the sphere, as much water comes in and goes out, right? So you have net flux equal to 0. This is the idea. Is that clear? So on Wednesday, we will write this in mathematical terms. You can write it either in integral form or differential form, but the idea is this. I like you to think always with this idea. You know, unless you have sources, that is charges inside the closed surface, the net flux is 0. It's very intuitive. I mean, either you produce something, or if you are not producing something inside, like water, like a faucet, then the net flux is constant because it's conserved, if you wish, right? It comes in, but then it also goes out. So this tells you something about the flux. How about the circulation of E? The other quantity that we... So circulation of E around a curve C, okay? Around C. Again, if you remember your Maxwell's, you remember that this is equal minus the time derivative of what? Of the flux of B through S, where S is the surface included into the circulation C. So you take a line C, and this has a surface S included inside the line C. So the circulation of E around this curve is equal to the time derivative of the flux of B through this surface, right? So immediately you know that if you have a constant field there, a constant B field, constant, you see then the flux of this field is going to be constant, and therefore the circulation of E will be 0. In fact, in electrostatics, that is the next thing that we will do next week, where everything is frozen, then the electric field is described by two simple equations, that the flux is proportional to the sum of the charges inside, and the circulation vanishes. Okay? So you see, it's very simple. It's vice versa, if you have a B field, right, then if this B field is varying, or if the C, the circuit, is changing, then you have a circulation of E around that. Yes?
I think in this case, all time the charge has to be not to be constant.
The charges?
Inside this.
No, this is just the flux of B across this surface S. So if you have a B field that is varying with time, or the shape of this C is changing, think of an electric motor. How does it work? How does it work? Something has to move because you have to generate some electricity from a magnetic field. And from this equation, you know that if everything is frozen, I mean, if the magnetic field is constant, then you get no electricity. And no electricity, no work.
Yes.
So there, typically, you have a magnetic field that is constant, but then you have something moving, like a square or something, or a wire that turns like this. And because it's turning, the SC crossed by the B field is varying. And this variation induces the electric field that is the current across the loop. This is the idea of an electric motor. That's what is moving everything in this room, everywhere, right? This simple equation is moving. But Maxwell, actually Faraday, before him, understood that you have something has to change because it's the derivative with respect to the time that link the B field at the electric field. You need something to change in order to induce the electric field. And the force, what is really doing work, is only the electric field. Therefore, you need this situation. Okay? How about the other? Then I stop. Let me just write the equivalent for the B field, and then we stop. So how about the flux of B? So the equivalent of this is flux of B, right? Exactly the same, through any closed surface, through any closed surface. A is equal 0. Always 0. That's great. This is a beautiful property of the B field. And what is this property? That there is no magnetic charge, in a way. Or better, there is no magnetic monopole. Because you see, this is the net charge inside. But here is always 0. So that means that you don't have the equivalent of the electric charge. You don't have a magnetic charge. This is people looked very hard to look for this, right? This is a surface, a closed surface. It's always 0, doesn't matter. Because it's always 0, that means that you cannot have the equivalent of a charge, because here, to make this different from 0, I put a charge inside this surface and I generate a field, right? But here it's always 0. I'm not telling you, so that means there is no magnetic charge. And this is a big asymmetry in Maxwell equations. You see, these two are not the same. The B field is very different from the electric field because this B field has a divergence always 0, as we will see. And this is reflected in a physical result that you don't have a magnetic monopole. And here you see already an example. If you think that the equations of physics must be beautiful, must be symmetric always, this clearly is not true, because here, if you wanted that to be symmetrical and beautiful, you would have put 0 here too. Or you have put something here different from 0. But that's not the way nature is. One is 0, the other is not 0. The B field is is a manifestation of the electric field, but it's different, because in nature there is no magnetic monopole, or at least we haven't found one yet. And you know that this is there has been a search for this magnetic monopole. Clearly they are not very common, like electric charges, but they haven't been found. So for the moment we stick to Maxwell equations, and here we put 0. Okay. You know that if you have a magnet, right, and the monopole will be a magnet that is very thin, and then you look just at one end, right, because one end looks very much like the North Pole without the South Pole, if you wish. But you know that then if you break that up, you are not left with the North Pole. You are left with the North and the South Pole. This is exactly the thing. No matter how you cut your magnet, you will always end up with the North and the South Pole. And so you get 0 here, in a way. This is a sort of simple-minded idea. But, of course, at the beginning, people thought that they were magnetic objects, and they thought maybe if you cut it in half, I get the equivalent of a positive North Pole, right? But you cut, and you get always a North and a South Pole. So then, eventually, you realize that you don't have the equivalent of a single electric charge. You don't have the single electric magnetic charge that is called a monopole. Okay, but how about the circulation of B around C? Actually, here you have to put a C square for reasons of the units that we pick. So C squared times the circulation of B around C is equal to, well, there is a term like this, is equal to minus. This part, yes, is symmetric. So is proportional to the variation in time of the flux of V through S, where again, S is the surface spanned by the circulation C. But again, the symmetry is not so. Indeed, it's true that as when you vary a B field, you get an E field. If you vary a E field, you get a B field. Albeit much smaller because of this C square. Remember, C is a pretty big number. So actually, varying a E field induces a B field, but much less than varying a B field induces an E field. That's why electric motors are made using this equation and not that equation. But again, here there is a slight asymmetry, because you also have a piece that looks like this, because it's the flux of electric current through S divided by this epsilon 0. So here you have to add a new concept, that is electric current. So you have charges, but also charges that move, making electric current. So if you have a flux, a net flux of electric current through S, so through this, okay, this flux gives you a circulation of B that is different from 0. And these are the actual equations. So please, I mean, this is really all you need to remember after this 20 lectures or whatever, the Maxwell equations. And in this form, I think it's very easy to remember. So next time, we translate this in mathematical expressions, because we need those in order to crank the handle and get the mathematical solutions. And then we will move on to specific problems, like what happens if everything is static. So we will study electrostatic and magnetostatic. then what happens if I'm varying slowly the B field, and so on and so forth. Okay? Questions? Okay. So maybe now is a good time for you to refresh your memory about vector calculus, because here we need to quantify this, what is this circulation, so you need to remind yourself what is to do an integral of a vector along a line, and what is to do an integration of a vector over a surface, because that is the flux. Okay, so that will give us Maxwell equation in the integral forms. Then we will use, did you do the Gauss and Stokes theorem? You remember that? So you did do, not here. Okay, so, well, refresh yourself also about Gauss theorem and the Stokes theorem. That you remember, they link, in fact, integrals along lines with integral over surfaces, because that will allow us to rewrite these equations that you see are in integral form, because I do integrals over surface, into a differential form that is easier to, I mean, the integral forms are easier to visualize, like here, but to work out the solutions is easier to use the differential forms. So go and refresh yourself about these things so that we go on speedily next time through the Maxwell equations.